Hello, I'm Patty Simpson with Simpson Math. In this video, we're going to look at irrational numbers so that we can graph those as irrational roots with our polynomials. So first, let's look at just square roots. We know that the square root of a perfect square turns out to be this nice number. So like the square root of 9 is equal to 3 because 3 times itself, 3 times 3 gives me 9. So this square root is just asking what times itself gives you 9. What times itself gives you 36? Well, it's 6. And we know those nice perfect squares and what their square roots are. But when we get ready to graph these irrational roots, we're going to end up with some numbers that are not quite so pretty. For instance, we may be looking at the square root of 7. Now the square root of 7, there is a number that it can multiply by itself to get 7. It's just not a pretty number. It's an irrational number. And so we are going to approximate. We're going to give you about how much it is. And in fact, if you put it in the calculator and you say, what's the square root of 7? You're really just getting an approximation because it's cutting it off somewhere, that decimal. We're going to approximate. We might not be quite as good as the calculator, but we're going to get pretty daggone close to what that actual number is that multiplies times itself to give you 7. And the way we're going to do that is we're going to use our perfect squares to help us. So notice that this 7 is between the 4 and the 9. So I know that the square root of 7 has to be between 2 and 3. 7 is closer to 9 than it is to 4. So I know that it's going to be closer to 3 than it is to 2. So, like 2.6-ish is about how much that square root of 7 is. That's about how much it is. So we've approximated how much the square root of 7 is. Let's do the same with the square root of 11. Notice that 11 is in between 9 and 16. So I know that the square root of 11 is going to be between 3 and 4. Closer to the 3 than the 4 because 11 is closer to 9 than it is to 16. So it's about 3.2, something like that. It's approximately there. If you look at the square root of 47, 47 is between 36 and 49. So the square root of 49 is going to be between 6 and 7. Closer to the 49 than the 36, so, almost 7. It's going to be 6.8-ish, maybe 6.9-ish, somewhere in there. The square root of 83, well, 83 is between 81 and 100. So the square root of 81 is between 9 and 10. Again, it's closer to 81 than to 100, so I know it's closer to 9. So maybe it's like 9.1-ish. So we're just giving an approximation of those values. We're approximating, and we're using our perfect squares to help us with these ones that are not so nice and pretty. Now we're going to be graphing roots or x-intercepts that look like this, where we have -2 plus the square root of 13, and then our y value is 0. -2 minus the square root of 13 is equal to 0. We're going to graph some things like that. Now I want to back up just a minute and remind you when you were in elementary school that maybe you used a number line to help you to add and subtract. So on a number line, if I want to add or subtract something like 5 plus 3, I can start at this number, 5, on my number line, and I can move to the right. That plus sign tells me to go to the right 3 spots. So, I jump over 3 spots, 1, 2, 3. 1, 2, 3 spots to get to 8. 5, 6, 7, 8. So maybe you used a number line to help you with addition. Maybe you used a number line to help you with subtraction. Maybe I'm doing 5 minus 2. Well, again, I'm going to start at the number 5. The minus tells me I'm going to go to the left 2 spots. So I'm still starting at that 5, but now I'm going to go to the left, down to 4, down to 3, down 2 spots. I went minus 2. So my answer here is 3. So we can use a number line to help us with adding and subtracting. Anytime I'm adding, I just go to the right. Anytime I'm subtracting, I just go to the left, and I start at that first number. So how does that help us when we're graphing these irrational roots? Well, when I have a number such as this, where I have a negative 2 plus the square root of 13, I can do that same thing, where I start at negative 2. I know I'm going to go plus the square root of 13. Well, about how much is the square root of 13? Let's go back to our perfect squares. 13 is somewhere between 9 and 16. So I know I'm going to go 3, somewhere between 3 and 4. 3 and a little bit. That square root of 13 is approximately 3.5-ish. So I'm going to go over 3 and a little bit. So from this negative 2, I'm going to go over 3 spots. 1, 2, 3 spots. So negative 1, 0, 1. And then before I get to 2, I'm going to put a point there. This is the point, negative 2 plus the square root of 13, comma 0 on my x-axis. Then if I want to graph negative 2 minus the square root of 13, I do that same thing where I start at negative 2, but now I'm going to go to the left, that same approximately 3.5-ish. So backwards, 1, 2, 3, and a little bit. So I'm at negative 3, negative 4, negative 5, not quite to negative 6. So that point there at negative 2 minus the square root of 13, comma 0. I've put those 2 points on my x-axis. We're going to graph some more in the future where I show you how we graph those x-intercepts. But notice all we do is start at this number. We go to the right, whatever that approximately is. Start at the number and go to the left about that much. So, and we just approximate, it's 3 and a little bit. 1, 2, 3 and a little bit. Back that same amount. 1, 2, 3 and a little bit. So I've graphed those irrational roots. In addition to that, we're going to need to remember how to solve for x in these type of situations. So here, remember when we have 0 and we have that x squared, we like to factor it. So let's factor this thing. We have 2 terms. It's a difference of squares, so I can use my difference of squares, and I can say the signs are going to be different, and that's what ends up with a 0 in the middle. The square root of x is x, square root of x is x, square root of 4 is 2. So that factored is equal to x plus 2, x minus 2. I'm going to set each one of those equal to 0. And I end up, my x values are at x equals negative 2 and x equals a positive 2. Notice that there are 2 solutions. We thought there would be 2 solutions. There are 2 solutions. I'm going to use that same strategy here. I know that 17 is not a perfect square, but I can still do this same thing with it. I'm going to pretend that it's a difference of squares, so that I set my 2 parentheses. I'm going to put a plus and a minus between them, so that when they multiply together, I end up with a 0x term. Then the square root of x squared is still x. But now that square root of 17 is not pretty. I'm going to write it as the square root of 17. The square root of 17. So there I have factored this. And if I were to multiply it out, the square root of 17 times the square root of 17 would give me 17. So that would multiply out to be x squared minus 17. Now I can set each one of those factors equal to 0. and solve, and I see that x is equal to a negative square root of 17, or x is equal to a positive square root of 17. So even though that wasn't a nice, pretty difference of squares, I can still factor it that same way by just leaving it as the square root of 17. We're going to use this and graphing of those irrational roots in the next video, where I graph a polynomial that has irrational roots. Math made simple at Simpson Math. Thanks for watching.